Okay. Hello, everyone. Oh, I'm Sam. Is it just me, or does that sound a bit strange? Okay. Thank you very much for coming to my talk. It's always good to have the slot that is right after lunch, so feel free to have the best sleep of your lives during this talk. um, this is the first time I've done this talk because I've been doing engineering for about 12 years, maybe 13. Been coding before that as well. And I've moved from being a traditional API developer, website developer, learning every new JavaScript framework every other week, to big data. And oh, I'm not getting. Let's have a look why that's not working. There you go. So moved from traditional web development to big data about 18 months ago. And the inspiration for this talk was to share some of the learnings I've had, because we're in quite a unique industry where we learn from our failures. No other industry out there has that. Like, you don't see a pilot that keeps crashing on takeoff continue to be a doctor to be a pilot for so long, and same for doctors if they keep killing their patients. But with us, the motto in our industry for such a long time has been fail fast, right? We want to get that failing test. So because of that, I'm here to share my stories and the pain points I felt, the failures that we had, and hopefully if any of you are interested to moving to big data, I'll give you a good example of what to do and what not to do, and the basic concepts that I had to learn as I go along. Out of interest, how many people here are actually like engineers in the room? How many are data engineers? How many work with data all the time? Okay, so a few. So I think that to start off with is why I moved careers, right? Why I moved focus, and the reason being is I think the unique selling point between company A and company B isn't tech anymore. It's not. It's not how well you do features. You've got companies like WhatsApp and Instagram that were sold for like billions of pounds because not because Facebook couldn't write a messaging app or add filters to their photos, but it's because of their data, right? It's because they really understand their data and they really understand how their customer behaves, and they build really good data products. So they're being bought for their data. And I think that's the differentiator between company A and company B. And even though we're in IT and everything we do are assumptions, we assume if we do A, we'll get B. I'm a strong believer in having data-driven decisions. As a side note, you can Google this story later on, but it's been attributed to Marissa Mayer, the CEO of Yahoo, but while she was working at Google. But the idea of the story was 50 Shades of Blue, then renamed to 41 Shades of Blue, and it has nothing to do with the book. But the idea was some marketing executive at Google said, we want to change the color on Google Ads, and we want it to be a certain shade of blue. And the developers were like, I don't know what this executive is talking about. So what we're going to do is we're going to deploy 40 other shades of blue. And they found out that if they kept the original shade of blue that was asked or requested by the marketing executive, they would have lost millions of pounds throughout the year. Because Google Ads, that's how they work. If you click on the ad, they make money. And that's a data-driven decision. So that's kind of why I moved careers. And when you ask yourself, well, what is big data? And there isn't really a good definition. I kind of like that tweet because it sort of summarizes the fact that it's just a buzzword no one really knows. But out of interest here, how many people think, 100,000 records is big data? 1 million? 10 million? 100 million? Well, the answer is it doesn't matter because it's about how you use that data. But when you're under hundreds of terabytes or petabytes, and you realize that you can't handle it, and that really is what big data. It can be handled in a traditional database. It needs to be distributed. But to give you a good idea, there's like big data is really if you had to give it a definition, it's 3 V's, and the first V is volume. How much data you have that is not manageable in one server, or you have to have a clusters. Another is velocity, how fast the data is coming. How often are you doing 10,000 orders a minute, 100,000 orders a minute, a million orders a minute? How fast that data is coming in? And the most important one, in my opinion, is variety. Is how many different data sources you have. You know, it's not just from one database. It's coming from an API. It's coming from a weblog. It's coming from click feeds and click streams. You've got so many different data points, and you've got your job as a data engineer is to consolidate all that and give it to analysts and to try and make sense out of it. So you can add the feedback loop. In most companies I've seen, the feedback loop's not there. They come in and say, we're thinking of doing this. They go to engineers, the engineers will build it, and then they go back to BI and say, how well did we do? Like, for example, you know, they'd say, well, let's implement social logging, right? We want people to log in via Facebook, to log in via Twitter. They'd implement it, and they're like, how did it? We think if we allow them to log in via Facebook and not need to register, they'll order more. And then they come back to BI and say, well, how did it do? And then BI have to work with their data engineers to implement that data feed again. So it's not the data slowly becoming a first-class citizen, but the feedback loop is still broken. So the first term that you sort of learn about is ETL, and it might be quite basic to everyone, but I didn't know when I first started that ETL starts for extract, transform, and load, which basically means you're taking data from one place and you're transforming it into the shape that you want your business to have it, and then you're loading it into the data warehouse. So traditionally, you'd be taking it, the extract is coming from SQL databases that are geared or designed towards transactions. So that's online transaction processing, OLTP. And these are databases that want you to write many ones, basically. They're designed from the ground up to be highly available, to be able to, so you're always able to write to it. While the data warehousing is geared towards analysis. Analysts are reading that, and they don't necessarily they're not looking at just one column, they're looking at all of them, and it's geared towards analysis, so they're sort of designed differently. And your job as an engineer is to get it from hundreds of different sources into one database or one data warehouse to allow the business to gather insight into what is happening in your business, how their customers are behaving. So that's kind of why I moved towards the data team. And I quickly realized a lot of the best practices that you sort of understand as an engineer in the DevOps world are just not happening for Python developers. So the data team at the time was just Python developers who were using tools that connect to SQL Server databases, MySQL databases, and pushes it to a data warehouse. They were hard-coded Python scripts on one box and one Windows machine hosted in AWS, and that thing took 8 or 9 hours to run. And it was really painful because the only way you found out when something broke was when you come in the next day and the analyst will tell you, it's broken, I don't have data from yesterday. And it was a really bad place to be, and don't hard code anything, really. That's the advice here. Another pain was new sources were extremely difficult to add, right? You'd come in and say, well, now we've implemented this new feature, and as the website grew, it was originally a one SQL Server source of truth, but then we had to break up the application, distribute it into microservices, and as you know, when you scale up that way, each set of services will have their own set of databases, because they need to scale well. They keep their responsibility. If I'm responsible for login, I will implement the Facebook login thing, and it will only be in my own database. So then when the analysts want to come in and say, well, how did we do? You're like, well, to be able to know how many orders were made via Facebook, you need to go to that database. So implementing that, ingesting that data was really difficult. And as you grew, the data wasn't traditionally in SQL databases. There were APIs returning JSON blobs. So you had to serialize it and then normalize it and then put it in the database. And it was quite a pain. It was a massive pain. And obviously the slow thing was excruciating, because even if you found out the next day there's a problem and you fix it in 5 minutes, it took 9 hours for the thing to run again. So that's the whole day gone for analysts not able to query the day before. So there was a lot of pain there. So the first thing we had to do was, we're like, we need to fix this, right? So we changed the ETL process that took 9 hours. We said, okay, what we're going to do is we're going to move it out of its monster Windows application that it's running on at the moment, and AWS will suddenly restart our machines because of security. If you guys don't feel that's important, you should look at the NHS recently. So we need to move that to become immutable infrastructure, to run in CI, and to run every 30 minutes, so we catch failures quicker, because they do happen. And what we did was we notify everyone to happen. So that was the initial step. That was a big push throughout 2 weeks to try and get this immutable, get it running faster, getting bulletproof. Right? We had a big point in the board saying we want this process to be bulletproof. The next thing we needed to do is make our data queryable. That was our underlining goal for this data pipeline, right? We want to make any point of data that we implement queryable for everyone. Anyone can get insights into this data. Whether the data is JSON, CSV, any sort of data format, you want it to be queryable immediately. And the most important thing is we need to be able to handle bad data. And that's the first pain point that we had. We needed to be able to say, okay, fine, moving data from A to B is easy, but what happens when the data is not there? What happens? What do the business users see? Do they see dashboards that when the dashboards are not updated? Is it because there was no data, or is it because of the was there a failure? Or we'd be able to handle places where we have schemas defined as a field, for example, was supposed to be a timestamp. We got a string, something that was a long. We got a Boolean. We need to handle these sort of scenarios. The second thing was obviously schema updates. We wanted to make it really seamless, and what we did there is we've used a data processing engine called Spark to help us handle this, and I'll show you that in the demo. But we need to be able to handle schema updates efficiently because we didn't want to wait on the feedback loop to tell us, actually, there's been a change and some engineers implemented this. We wanted to be able to make things discoverable and constantly updated. So it's very, very low touch from a data engineering perspective. So, and the most important thing is we added alerting behind it. So we added initially the alerting to all ports, whether it was HipChat, Slack, emails, PagerDuty. We added alerting so everyone knows when something fails, so we're able to handle it much, much faster. And that's one of the most powerful things we did actually initially. Is because we wanted to catch failures faster, which means we resolve them faster. And we never got people coming in to say, oh, why is that table not updated? They're already aware of what's happening, and we had massive dashboards around our tables. So there are a variety of different data formats that you have to handle as a data engineer. CSV dumps going to S3, going to FTP servers, that's your bread and butter, you have to handle it. But then when you're dealing with different APIs, you've got JSON, and you've got to be able to handle JSON. And even though JSON's really easy to handle, when you think about how you're going to save it to make it queryable, that's when it becomes a little bit difficult because of the fact of there isn't really a way of ensuring JSON schemas. So you can get something that's not even a formatted JSON, you have to handle it. The next two things I never really understood at the time because I never really had to experience them was Parquet and Avro. And they're columnar-based storage, and I'll explain what columnar storage is in a second. But really, it's because you can edit 20 megabytes of JSON in your editor, that's fine, so you can look at it. But what happens if you've got 500 gigs of data being sent to you? It's not very easy to open that in an editor. So Parquet and Avro are formats of dealing and storing this data in a columnar format to make it much more easy to manage. And columnar storage is basically, traditionally you're saving the entire row in any place. With columnar, you're saving the column. And the reason why you're saving the column is because the discrepancies between the value or the changes within the value are very, very small. For example, you can have a Boolean column. The values there are always going to be either true or false, or a timestamp column, or a long. So that means the compression that you can do on that column is actually a lot, because you know what the data will always look like. That helps you compress data better, which makes it more manageable and makes it queryable easier. So that was really useful. And a lot of pretty much 90% of any big data technology that you deal with, it will be storing it in columnar storage. Apache Spark is something we've heavily implemented as well. There's so many reasons why Spark will make your life easier, and it deserves its own talk. But to give you a very, very, very oversimplification, there's two things that Spark really gave us. We had analysts that only speak in the SQL world. They don't know any coding. They don't know any Python. Some of them might know Python. We had engineers that work with Python and Scala, and they're comfortable with it. And we had data scientists that only work with R. And working on getting a technology that encompasses all of them to talk on the same language as the business. They're trying to speak the business language and talk about terms within the business is very difficult. But Spark gives us that. We're able to express queries. We're able to express questions in that language interchangeably, and that's perfectly fine with the same data structure. It also allows us to talk with multiple different data formats. But really, the best thing about Spark is the fact of how it handles failure, how it distributes the data within its clusters, and it takes care of problems that people much smarter than everyone handled, right? People that spent 30 or 40 years dealing with it. So it makes copies within each and every worker node to say, okay, if it fails, then I know there's another node there that has another copy of the data, and you'll make sure your data is always correct. And that's a pain to handle within your code. It's probably something you want to avoid. We also implemented a workflow manager. This is actually one of the easiest things we did, and it took so much complexity from the code away. And really, what a workflow manager does is if you consider you have view X, right? You want to create this table X that has so many different data points with it to create this view of your business. And this view X has dependencies on table A, B, and C. But table C has dependencies on table 1, 2, and 3. So in the code, what you used to do is like, actually, I can't build X till I build those 3 tables, and I can't build that 3rd table till I build the first 3 tables. So it's like a dependency tree. And a workflow manager will just say, will do things like make sure that it stays correct, add things about alerting, add things about retries and backoffs, and you can program that all into workflow manager and it makes it so much simpler to worry to design this graph. It's called a direct acyclic graph, or a DAG. It's much easier to define this dependency tree to help you deal with complexity in your code, and actually makes parallelizing them really easier, because now you've separated your tags to different DAGs, and it helps you speed up your process. So part of a data pipeline isn't just ensuring that the data goes between A and B. There's also a data serving layer. And we were using Redshift, which is the data warehouse that comes with AWS. The problem we faced is Redshift is extremely easy to use, and you'd think that that's not really a problem. But you need a lot of expertise when you're sorting out things like indexing. So you get things like disk keys and sort keys. And what these are, disk keys is a distribution key, how you're going to save that data throughout your cluster. And the sort keys is how you want to sort that data around. So your typical sort key would be your date. And if you get those wrong, when you're querying millions of records, it becomes very, very slow. And the most important problem that we faced is the storage and the compute are not separate. So you're storing all your data within the same cluster, and you have the same computing power. You can scale up, but it's both expensive, and you have to put your cluster in read-only mode for 12 hours. And we had ETL running all the time. But to give you an explanation of the problem, say you had a data scientist who was trying to create a machine learning model over the past 5 years, and you had an ETL load updating the existing results, and you had an analyst who was creating dashboards for the business metrics off the same cluster. They're all running in the same data warehouse, but you don't want to explain to the business user that your dashboards are running slow because the data scientist is running heavy loads on the queries. Like, he's really taking a lot of power. Or you don't want to explain to your manager that data scientist, she's busy trying to build a particular machine learning model over the past entire history of the business. So these are separations of concerns. And we wanted to build something that can scale up really fast for each and every need, basically. So Redshift's perfect for dashboards and business BI, business insight or business intelligence. It's really powerful for that, but it's not necessarily the best tool when you're dealing with on and off clusters on demand. So we kind of started off building this Lambda architecture, and what Lambda architecture is you're separating two concerns here. One being the batch layer, or the slower layer, or the 30-minute interval, and one being the speed layer, which is the streaming. So if you think about that as that is your incrementally updating updates of data every day, every 30 minutes. But here, the speed layer is the streaming, something that happening in real time. So a hashtag that's trending on Twitter, that's streaming. That's in real time. You don't want a hashtag that's trending 6 months ago. You want to know what's happening now. And a good implementation of what we did for the streaming layer is X amount of people are looking at this product in the past 5 minutes. It's really short-lived data, but it's really interesting to try and build data-driven products off that. Or X amount of people have bought this item recently. It gives you really deep insight into what people are doing right now on your platform. So that's a really basic explanation of streaming. There's a variety of streaming platforms out there. Kinesis is one of them. Kafka is one of them. But the concept of a stream or a streaming pipeline is you've got a producer of data, you've got a pipeline, and they've got the consumer. If you take Twitter as an example, you as a person, you tweeted, you're a producer, and then Twitter's a pipeline, and then someone who's following you is the consumer. And that's basically it in a very, very big nutshell. But we had problems, right? We had problems with the fact that we went to our CTO and we said, actually, we need about £100,000 for the next 3 months to build a Kafka pipeline, because it will help us build this massive data pipeline to enable the business to gain insight and make data a first-class citizen. The problem there is we needed a team to manage it. People just don't produce streams. It's what you do with those streams later on to build them. And for you to build the streams, you need the producers to produce the data. So you need to enforce in the entire business to make sure any data you provide, it's being pushed to that Kafka pipeline. So we had problems convincing people to say what are the benefits of that. If people don't produce, then there are no benefits. There won't be any consumers to consume the data if no one's tweeting, as an example. That's sort of why Spark came up with the idea of a continuous application. They realized that it's not about creating the data, doing your transformations, and putting it into a sink. You're actually also running ad hoc queries on your stream. How many people are looking at it, looking at this product at any given moment, as an example? Wow, that's very fuzzy. It's not meant to be, but you can get that exact picture from Databricks. They're the guys who created Spark. But yeah, not only you're creating streams, you're running ad hoc queries, and then you're saving into another data store. So they came up with the idea of structured streaming, which will continuously monitor a particular HDFS location like S3 or Google Storage, and it will then write that data to an output sink. You can also write it to a database. You can also write it to your data lake, but you can also run SQL queries over it at all times. What was really beneficial is it then takes care of things like retries. It takes care of things like failure. All you have to do is write it to S3, and then that lowers the border the border of entry really to a much lower scale. From having to implement Kafka clients to writing to S3, that's much easier. People, if you can force that, you can ensure you write your data to S3, and we will make it queryable. That's a much more achievable goal. The warning slide is because structured streaming is still in alpha. So we're using it for things like logs to prove that it's scalable. So we're currently doing about 100,000 a minute, more or less. It's actually it's very reliable. The issues that we face is some of the APIs calls that we're making, like the filter calls that Spark gives you, and I'll show you some of an example, are not transferable into structured streaming. So there's a really useful method that says drop duplicates, and that isn't necessarily transferable to structured streaming. You can do it in a stream, but you can do it in a data frame. And those are the sort of issues that we faced. But those are quickly being resolved. Drop duplicates actually, I think, got resolved with the latest deployment of Spark. The next thing we wanted to implement is Google BigQuery. Because the BI team were already using Google BigQuery with ads. Is out of interest, anyone here using Google BigQuery? Oh, okay. So we've got more people going. That's good. It's really useful. You can run terabytes of data within seconds. It's really, really powerful. The caveat here is you're paying per query. So I think the last time I checked, it was $5 for 1 terabyte of data. So if you query 1 terabyte worth of data, it's $5. But that's only when you pay. You never pay for pushing that data through. Although you kind of pay a 0.001 cent per gigabyte. But the majority of your costs are going to be in your query, and it's really, really cheap. What you're doing, what it gives you is you abstract away the knowledge of needing to know indexing, needing to know about sort keys and disk keys, and hiring a team of DBAs to actually ensure your database is running smoothly and returning queries within seconds. People don't want to wait. You get this problem because as someone who doesn't know anything about the database, the first thing you do is you do select star in your database. And that's really bad when you're doing columnar storage because you're getting all the columns that are saved all over the cluster. And even if you're limiting them, give me all the records by 5, you're still having to go to all the cluster to get that data instead of just what you need. Like Google BigQuery sort of saves that. But a very nice thing we found is when we're querying JSON, or because we're getting JSONs from some of our API, we're able to get the nested structure. So JSON, as I'll show you in the demo, can be nested. You can have a big JSON blob within a record within a record. And what you need to do if you're saving it to a normal database is you need to normalize it. But with BigQuery, you don't have to. You actually save the entire thing and you get a record structure. Then it makes it much more easily, much more queryable. It moves data from being JSON. It may be very difficult, even if you're using Elasticsearch. If you ever had to explain to like a BI analyst how to use Elasticsearch, it's very, very painful. They are much more comfortable with SQL. So if you give them an ability to query JSON by SQL, it's very powerful. But another really cool thing is that this enabled us to do recommendations. It was the first recommendation engine I wrote was based on the ALS metric, which, to give you an example, say I go on the weekend, my name becomes Samantha, and I tend to buy I use foobar.com to buy my clothes. And say I bought 6 things over the past month, or 9 things over the past month. What we can use is you can use a recommendation engine to build a matrix of what all your catalog, all your items, against all your customers, and find the intersections between people. So if I bought 9 things and someone else bought 10 things, if my 9 things are the same as their 9 things, I'm more likely to buy their 10th thing. It's very similar to Amazon's people who bought this also bought that. It's exactly the same, but with much more maths in the Amazon side. But the maths just gives you a more accurate picture. But the concepts of it is you're trying to build your recommendations based on the data you already have, or the data of your the behavior of your customers. So I'm just going to give you a demo now. Let me try mirroring my displays. Right. Okay, that's not very good. But okay, so I've got this JSON there, which is an example of JSON blob that I can get from an API, right? It is it's nested, right? So I've got one level here, then I've got an order container which has another JSON blob inside it, and then application info which has another JSON blob inside it, and then you've got order, and your job is to make this queryable to users. So traditionally you try to save it, shape it in the format you want, and save it into a database. Maybe you would have it structured where you would be like you'd have foreign keys all over the place, and that isn't the simplest thing you can do. So what Spark gives you, and this is Databricks. If you haven't used Databricks, really cool. You can use Zeppelin to do the same thing, pretty much. But we can then read in the JSON. I've got the JSON in S3, and to give you an example of where it is, this is it. It's just literally an orders blob in S3. And what you can do is then you can print the schema of the data frame. And this schema is exactly that schema. It's exactly the same. But then, now that you've loaded it in memory into the cluster, you can display it. You can display what the data frame is. You can say dot select just customer ID. Should be exactly the same, giving you that. But you can also run SQL, right? You can just say, okay, I'm going to switch to SQL now, and I want the order container, the application info.user engine from this sample JSON. So it should return that line there, which is Mozilla iPhone. So if you look at that, yeah, Mozilla iPhone. It's really interesting that is now that you saved it to Spark, this is all still in memory. It's not really queryable by the end user. But then you can now use structured streaming to say, okay, what I'm going to do is I'm going to monitor. So that's my code here. What I'm doing is I'm monitoring an S3 an S3 key or an S3 folder. And what it's going to do is anytime you upload a file to this S3 folder, I'm going to save it to Spark. I'm going to load it, to Spark, and then save it to BigQuery. Which means I can have this running all the time, or you can run it once a day, whatever you want. It's unifying the batch and streaming model. And all I'm doing is I am then saving it to a table. The table name is there, Riga Dev Days. So if we run that, there you go. If we run that job, what's going to happen is it is going to keep monitoring that S3 file, S3 file folder, and try and look at all the JSON blobs that are that are currently in the key or in the folder itself, and it will then save it directly to BigQuery to make it queryable to users. So if we look at where am I looking for the start stream? Yeah, see that's the schema of the JSON that we uploaded. It's creating the table. So if we look at BigQuery here, and we reload the page. There. So now you've got, you've got the entire schema here. Let me try and zoom out. So you've got the entire schema. And this is queryable by users now. You can tell you how many details. At the moment there's only one record. But what happens if you've got this thing running now? What happens if suddenly your API wants to, we're going to copy exactly the same file again over to S3, but we're not going to touch the streaming application, right? And now, if you look at this streaming application, if you look at the logs of what's happening, is it's looking and it realizes there's a new file that's been added to the S3 folder. And all that is being done by Spark, so you never actually have to worry about it. You just point it to a folder, and you tell it where you want to checkpoint. And I'll explain checkpointing in a second. But if you then reload this page, you should have 2 records come in. When it loads, 2 records. Now, what happens if you kill the streaming query? Right, so I'm going to kill that. And I'm going to run it again. It's going to use the checkpointing directory to say, what was the last record, or what was the last batch ID that I read? And it says, okay, it was 2. So you shouldn't find duplicate records. It will only point to the last point it saw. So if you refresh this page, I shouldn't have more than 2 records, the original 2 records that I have. Yeah, there you go. So that solves the problem of making it queryable. But what about schema updates? So imagine I've just implemented the is Facebook login on the same JSON. The API now returns that new field. What happens is, and then what we're going to do is scale that, and what we're going to do is copy that new JSON Where are we? Orders 2. Okay, let's call this orders 2. And we're going to save this JSON that has is Facebook login. And you can see from the schema, it doesn't have is Facebook login because it doesn't know it existed yet. So what we're going to do is we're going to copy that file, start the streaming query, and what it's doing is, as you can see, it normally comes at the end, but it won't have this because we just added it. And what we're doing is, hopefully, when it processes this file, we should have 3 records, but we should have 3 records with the new schema. Yeah, so we've got customer ID. Did it save it? No, it's still under 2. Just waiting for it to load. Yeah, so we've got 3 records now. And you've got is Facebook login now. That's a Boolean because it figured out from the JSON that it's a Boolean. Notice that I didn't actually do anything about schemas. I didn't hard code schemas. I didn't tell it anything about the schema. It just automatically reads the JSON. And it's the same for Parquet, it's the same for CSV, it's the same for Avro. It just makes it much easier to deal with it. But you ask yourself, okay, well, Sam, that's what's the size of the table? That's 3 kilobytes, right? What happens if I want to run it over over the entirety of GitHub, right? So what I'm doing here is let me just format that query. So what I'm doing here is I'm taking things like I'm looking at all the commits ever in GitHub and getting the author, the commit name from public GitHub, and I just want to run against my commits. So if you run the query and you look at, it's going to process 147 gigabytes of data, and it just 7 seconds. You can make it ridiculously big by doing star, and it's going to look at all. Again, BigQuery is also a columnar storage, and what it's going to do is now it's going to run 687 gigabytes of data. There you go. So I wonder how long that one will take. I do not think it should take more than 20 seconds. But we'll see. Don't fail me now, BigQuery. No, 19.4. How lucky was that? But you can look at the commits. There you go. So that one, if you look at what the commit name was, that's pretty much okay. It's my repository, but you can see I probably Spark somewhere there. No, that's me. It's not showing everything because it's there you go. Some of them are to the Spark GitHub, the Spark repository itself. I recently contributed to Spark, but the point is, this makes it much easier to query against it, and BigQuery will handle that. And that cost me less than $5 to query that. Actually, it was free because it's first terabyte's free. But the point is, you're abstracting away that knowledge of having a DBA or a team of DBAs, and the results always come back fast. You won't find another technology that returns terabytes of data within seconds. So that's the end of the demo. And you're welcome to ask questions if you have any. Okay. Thank you very much for listening. Have a great day.